All right. I get that people are struggling with that R1. It did go a little bit further than I thought, and I kind of figured that people would be able to use that Pythagorean theorem. All right. So up on your screen is very basically what we went over last class. That's the right triangle trig, that's SOHCAHTOA, that's sine, cosine, tangent, and then what those triangles would look like. All right. Um, as people kind of come in, um, first, I love that you guys are asking a whole bunch of questions about it. All right. That's awesome. But here's kind of the expectation going forward. If you didn't start that homework like right after this lecture ended, that needs to happen so we can address these questions a lot quicker than we are right now. Okay, so that's what that time in Teams is for. All right. Um, that's so I can kind of gauge about what I need to go over the next time. All right, this is fine, but let's use the entire period that we have in order to get to really know this stuff. Okay. Um, so two things I kind of want to review, or well, three things. First is this right triangle trig. The second is the Pythagorean theorem, and then third is rationalizing, and in general, just kind of dealing with rationals or radicals. Okay, so first thing, Pythagorean theorem. All right, and a Pythagorean theorem only has to do with right triangles, so this is exactly what we're talking about um, for the next couple weeks at least. All right, so when we have a right triangle, we have that the side opposite the right angle, that's the hypotenuse, and then we have two other sides. We'll say this is the angle, so this is the adjacent side, and then the side opposite the angle is the opposite side. All right. Um, this follows the rule that the side lengths of the opposite and adjacent squared are equal to the hypotenuse squared. All right, so using that, if you're given two side lengths of a right triangle, you should be able to find the third. I get that there's some radicals mixed in there, and sometimes it's a little bit tricky, uh, but overall, we should be able to do that. All right. Uh, and then the other thing is just in general dealing with radicals. All right. I'm going to use the example we did last class. So square root of 12. All right. We can rewrite the square root of 12 as the square root of the factors of 12. All right. So if we pick a couple of different factors, um, we want to pick the one with a perfect square in it. So let's just down here, we'll do factors of 12. So there's 2 and 12, sorry, 2 and 6, 1 and 12, and 4 and 3, right? And we have to kind of look at those factors and determine which one has a perfect square. And a perfect square is something that can be gotten by multiplying something by itself, right? So 2, you can't multiply anything by itself to get 2. You can't multiply anything to get by itself to get 6. So these two are out. 1 and 12. 1 is kind of a perfect square, but we generally don't consider it because 1 times 1 is 1. But nothing times itself is going to be equal to 12. So we're going to cross that off the list. 4, 2 times 2 is 4. All right. So the square root of 4 is 2. So let's use this set of factors. All right. So we can rewrite square root of 12 as the square root of 4 times the square root of 3. And we know that the square root of 4 is 2, and the square root of 3 doesn't simplify any further. So then this is our answer. Okay. That's kind of like a really basic example, and we'll go over slightly harder stuff here in a minute. But that's the general idea of it. If you have a bigger number, say something like 20, all right? And I know that's not a huge number, but we can work with it. We kind of do the same thing. If we have the square root of 20, we can get factors of 20. Or what I usually do is just keep on taking out 2. Okay, so we can rewrite the square root of 20 as the square root of each of these factors. And whenever something repeats, they come together to just form that one number, all right? So these square root of 2's, they repeat, so they come together and just form 2. And then we get 2 root of 5. All right. So are there questions about what's on the screen? All right, so we have to use all these tools in order to solve some of the questions in IXL. For right now, I'm going to use a couple of the examples that are in on campus, kind of on that harder portion. So on that second handout, we have number 8. Where we have this diagram with 2 sides, one is 16 and one is 20, and that bottom angle is angle theta, and we're asked to find the tangent of theta. All right, now from SOHCAHTOA, which I'll write over here, we know that tangent is opposite over adjacent. And on this triangle, we're given the hypotenuse and the adjacent side. So we don't have the opposite. So we need to solve for the opposite. Okay, so if we have our original equation, and then just plug in what we know, we can solve for the unknown. Are there questions about what I have up on the screen so far? Okay, then we have to solve for that opposite. All right, so the first thing we need to do is subtract 256 from both sides. And we get that the opposite squared is equal to 144, which isn't just the opposite. So we just want the opposite, not the opposite squared. Okay, so what this says is that something times itself is 144. So in order to undo that square, we'll get to that radical here in a second. Okay, but if this opposite is squared, in order to undo that, we have to take the square root of both sides. Okay, so then that leaves the opposite on its own. And the square root of 144 is just 12. Okay, so now we have the opposite and the adjacent. So we can say then that the tangent of theta is equal to 12 over 16, which is equal to 3/4. Okay. Without going any further, are there questions about this problem? Does everyone understand how this works with the Pythagorean theorem? How do you know which one is the opposite and which one is the adjacent? Okay. So that is dependent on where this angle theta is. Okay, because this angle theta is right here, because this theta is right here, right? The side attached to that angle theta, that is not the hypotenuse, that's the adjacent side. If you drew a line from theta to the other end of the triangle, that's the opposite side. Okay, so when the angle theta isn't there, say that these were marked A, B, C. We would be asking for the tangent of C. Right, so the vertex can be labeled as an angle. Is simplifying necessary for more complex problems? Yes. How do you square a radical? Again, so if we have something like the square root of 4 squared, by definition, this 2 right here tells us what we're multiplying by, all right? So this, we could rewrite this as the square root of 4 times the square root of 4, which is just 4. Okay, so usually when you square a radical, you're just getting rid of it. Is the opposite always 144 or 12 squared? The opposite is 12. In this case, it's not always like that. All right, I'm going to move on to a slightly harder problem. uh, let's keep going on problems, and you'll kind of, when you need to simplify it, usually you can tell. Uh, if you always need to check, basically, if you need to simplify. If you can't simplify, then you can just stop right there. If you can, though, you need to try. Like, there are some kind of weird looking numbers that seem like they wouldn't be able to simplify, like the square root of 51. Um, but you can't actually simplify that. So you just got to plug numbers in. You got to try and take as many factors out and just see if those factors are perfect squares. We literally just went over that. That's when you, okay, simplifying radicals. That's this right here. Okay, you try and factor the thing inside and then pull out perfect squares. Okay, this is number 11 on your worksheet. On that second worksheet, I did phrase it a little bit differently. Originally, there's a theta here, but we're going to get rid of that because this looks a little bit more like IXL. Okay. So in this diagram, we're trying to find the cosine of A. So we're trying to find the cosine of this angle. The worksheet in on campus that we've been going over the last 2 days. Okay. Yeah, this worksheet is in on campus. I told you about this last class. It's not for homework or anything. It's just a bunch of examples. All right. From this diagram, we need to find the cosine of angle A. And we know that cosine is adjacent over hypotenuse. In this diagram, we are given the hypotenuse and the opposite side. So we need to find the adjacent side. All right, again, in order to do that, you plug in to the Pythagorean Theorem. And then plug in the things that you know. Okay, so the opposite is 3. Okay, and then we have to solve for that adjacent side. So 3 squared is 9. And then we have to simplify this 3 root 2. And I'm going to do this on the side so you can see what's actually happening. This 3 square root of 2 squared, again, this 2 tells us what we're multiplying, how many times we're multiplying that thing in parentheses by itself. Okay, so we can rewrite 3 root 2 squared as 3 root 2 times 3 root 2. Okay, and then we just combine like terms. All right, so these constants on the outside, the coefficients, we can multiply those two things together. So 3 times 3 is 9. And then square root of 2 times square root of 2 is just 2. So then we have 9 times 2, which is equal to 18. And then we can finish solving for the adjacent squared. All right, so we have to subtract over the 9. And then take the square root of both sides. So if we take the square root of something squared, that's just what's inside. And then the square root of 9 is 3. And then we can plug this in. And that looks like you're done. But that is not a rational answer. Okay? So whenever you have a square root in the denominator, that is not a rational fraction. And in order to rationalize that, we have to multiply by a clever form of 1. Okay? In this case, in order to cancel out that square root of 2, we have to multiply by root 2 over root 2. And what that does is gets us 3 root 2 in the numerator, and then 3 root 2 times root 2, which just becomes 2 in the denominator. And then we can simplify that 3 over 6. And then square root of 2 over 2 is our actual answer. Are there questions over this problem? Sometimes in IXL it's said to multiply 3 in the top 2, the 2 on top. That, I think, That's saying you multiply 3 times rad 2, which is just 3 rad 2. All right, couple more. All right. So given this diagram, so we have triangle RSQ, and we have side lengths 4 rad 2 and 3 rad 6. Okay, and we want to find the sine of Q. Okay, so we're dealing with this angle right here. So sine is always going to be the opposite over the hypotenuse. But we don't know the length of the hypotenuse. We don't know the side opposite the right angle. Okay, so we need to find that. Again, we can plug that in to our Pythagorean theorem. And before we do that, I think we should probably label which side is which. All right, so for Q, if we drew a line from Q to the opposite side of the triangle, this 4 rad 2 is our opposite. And then the side attached to Q, that's not the hypotenuse, that's the adjacent. Okay, so then when we plug all those numbers in, we have 4 rad 2 squared plus 3 rad 6 squared is equal to the hypotenuse squared. Okay, and then we just solve for the hypotenuse. Okay, so 4 rad 2 squared we can rewrite as that. 3 rad 6 squared we can rewrite as that. Okay, now we have to simplify the left-hand side. So in blue, 4 rad 2 times 4 rad 2, we can do 4 times 4 first. That's 16. And then rad 2 times rad 2, that's just 2. Three rad 6 times 3 rad 6, we multiply the 3's first. That's 9. And then rad 6 times rad 6, that's just 6. So then 86 is equal to the hypotenuse squared. Now, we have to simplify this after we take the square root. So I'm going to move up here. So you have to take the square root of both sides. Then we have to simplify that radical. So I'm going to do kind of the long way. And just take out 2's. I actually think that's about as simplified as you can make it. Yeah, I believe that's as simple as you can make it. All right, so then we have the sine of q is equal to the opposite, which is 4 root 2, over the hypotenuse, which is square root of 86. And then we need to rationalize that. You do always have to. At least you always should. I think sometimes radicals, though, aren't simplifiable. So like the square root of 86, there's no perfect square factors of 86. So that's as simple as it would get. All right, so then we rationalize it by multiplying by the square root that's in the denominator. All right, so now this is almost our right answer. We would just need to simplify it a little bit. So I'm going to make a little bit more room. First, I'm going to simplify rad 172. So if we factor out 2's from 172, we can do that twice. Because the square root of 2's repeat, this just becomes 2 rad 43. All right, so the square root of 172 is 2 rad 43. So we can rewrite 4 rad 172 as 4 times 2 rad 43 over 86. Which is equal to 8 rad 43 over 86. And And then finally, that would be our answer. Okay, I'm going to shrink some of this so you can see it all in one. Okay, that is a lot. Are there any questions over this problem? Okay, we can either go. Well, let's do one more example. All right. So this question says to find the cosine of I, which our job is actually made a little bit easier because we have all the sides. All right. First thing we should do is we should just label what side is what. All right. So because we're dealing with this angle, and this is our right angle. First, we know that this is our hypotenuse. And the side attached to the angle that is not the hypotenuse, that's the adjacent side. And if we needed the opposite, if we drew a line from I to the other side of the triangle, that'd be the opposite side. But we don't even need that because cosine is just the adjacent over the hypotenuse. And because we know those sides already, we can plug them in. And when we do that, we get 9 rad 34 over 18 rad 34. And you should be able to see that there's common factors on both the numerator and the denominator. All right. So if we were to factor out square root of 34 from each, those two things would just cancel. And we're left with 9 rad 18, or sorry, 9 over 18, which is just equal to 1/2. And then you're done. That wasn't very hard. Um, so let's do one more. And this problem says to find the sine of angle Z. I mean, Jonah, I feel like that did have big radicals and big numbers. Usually, though, they look way more complicated than they actually are. So the first thing is just labeling whatever your side is, and then labeling what you have and what you need. In this case, we had everything we needed. We just need to put it in a fraction and then simplify. Okay, but for this problem, we want the sine of Z. So the first thing we need to do is to label the sides we have. So the side opposite the right angle, that's 6 rad 2, so that's the hypotenuse. If we drew a line from Z to the opposite side of the triangle, that's the opposite side. And then the side attached to Z that's not the hypotenuse, that's the adjacent side. And sine is always going to be opposite over hypotenuse, which we already know both those things. The opposite is 3 rad 2. And the hypotenuse is 6 rad 2. And again, we can really quickly just cancel things out. So rad 2 over rad 2, those cancel. And then 3 over 6, that's just 1/2 again. And I'm going to say this, it's not always going to be 1/2 like the last two were. But usually when you're given problems like this, they look a lot messier than they actually are. Okay, we'll do this and then we'll end this lecture and then go to teams. So we want to find the sine of y in this case. All right, so again, just as a general rule of thumb, the first thing you should do is label the sides that you have. Okay, so the side opposite the right angle, that's the hypotenuse. The side adjacent, sorry, the side attached to the angle, that's not the hypotenuse, that's the adjacent. And if we drew a line from y to the opposite side, that's the opposite. So we have the adjacent hypotenuse, we don't have the opposite, which we need to find. And in order to do that, we have to plug it into the Pythagorean theorem. And what's good, so if you ever have square roots as just side lengths, they usually cancel out in the Pythagorean theorem. All right, so when we simplify this expression, right, 2 rad 105 squared becomes 2 rad 105 times 2 rad 105, which simplifies to 4. So 2 times 2 is 4, times square root of 105 times square root of 105 just becomes 105. So that's 4 times 105, which is just equal to 420, right? 4 rad 35 times squared just becomes 4 rad 35 times 4 rad 35. 4 times 4 is 16. Rad 35 times rad 35 is just 35. And then 16 times 35 is 560. Oh. And then we need to solve for the opposite side. So 560 minus 420, that's 140. We need to take the square root of both sides. That cancels out this squared. And we have the square root of 140, which we need to simplify. All right, so again, I'm just going to do 2's. So square root of 140 becomes 2 rad 35. Okay, so if we make a factor tree of 140 and we just keep taking 2's out, we can rewrite 140 as 2 times 2 times 35. So our opposite is 2 rad 35. All right, and then sine is opposite over hypotenuse. So we have 2 rad 35 over 4 rad 35. Those rad 35s are in common in the numerator and denominator. So we have 2 over 4, which just equals 1/2. Okay, I know this can be intimidating with square roots and all these different equations. So you need to know SOHCAHTOA, you need to know the Pythagorean theorem, and you need to know how to deal with radicals. I get that that can be intimidating. As long as you stay organized and kind of go through this process, it takes a lot of the math out. Okay, sometimes the only real math that you're doing is simplifying a radical, which really at its heart is just factoring. Okay, so I'm going to leave this up for a minute or so, and if you guys have any questions over any of this, any broad questions, go ahead and ask them. Okay, and then I'll go over to Teams for a couple minutes, and if you have more specific questions, we can ask them there. Okay, so I'll leave this up for a couple minutes and go ahead and ask your questions. Okay. What about the ones where they don't cancel out? If they don't cancel out, you still need to rationalize. All right. So say at the end of everything, we just had like sine of theta is equal to 2 rad 7 over 3 rad 8. Those don't cancel out, but your answer is still not rational. Okay, so we need to rationalize it. And we would do that by multiplying by rad 8 over rad 8, which would be 2 rad 56 over 3 times 8. So it'd be 2 rad 56 over 24, which would be rad 56 over 12. Okay, so if they don't cancel out, if those square roots don't cancel out, you still need to rationalize the denominator. Is it okay if we finish up the Excel later today? Uh, Ideally, you guys started this at about 60 today. I would like this done very soon. All right. And by soon, I mean, I think I meant to give you a little bit more time to work on this. Um, I'd like it today. All right. So if you don't have it finished today, you need it finished today. Is homework finished? Yeah. That it needs to be done today. Okay. So I'll hop over to Teams here in a minute. Uh, and then I'll help you guys there as well. All right. So I'll close this and then I'll be in Teams here. I'll start a meeting and you guys can ask specific questions. So I'll see you there. There is no other homework. This is it. We need to get this down very well. All right. So again, I'll start a meeting here in a second and I'll see you there.